3 men are breathing inside a spacecraft built for 2. Every breath adds carbon dioxide. The lunar module can remove it, but its cartridges are running out. Across the tunnel, the dead command module has plenty of lithium hydroxide. Its filters are box-shaped. Aquarius uses cylindrical cartridges and a different airflow circuit. Nothing mates. The famous square peg in a round hole will not be pushed through anything. NASA has to make the air go around the mismatch before the atmosphere becomes the next failure. Apollo 13 left Earth on April 11, 1970, bound for the Fra Mauro Highlands. James Lovell commanded, with Jack Swigert in Odyssey and Fred Haise in Aquarius. At 55 hours, 54 minutes, and 53 seconds, the oxygen tank incident ended the landing. Oxygen pressure collapsed, the fuel cells lost their reactant, and Odyssey began losing electrical power. The crew activated Aquarius as a lifeboat. They had a route home, but its resources had been budgeted for 2 astronauts on a short lunar stay. Now it had to support 3 men around the moon and back. Breathing consumes oxygen, but exhaled carbon dioxide also has to be removed. Fans pulled cabin air through cartridges packed with lithium hydroxide. The chemical absorbed carbon dioxide, cleaned air returned to the cabin. The cartridge did not create oxygen. It stopped the crew's own metabolism from turning a sealed cabin toxic. After Aquarius was activated, its primary cartridge ran for about 27 hours, 82 man-hours of use. 3 people were consuming capacity, rated in human time. Oxygen, water, and electricity could remain while the cabin air became unusable. Odyssey carried replacement cartridges, but Apollo had not been designed for this transfer. The command module used box-shaped filters. The lunar module used cylindrical ones. Each belonged to different ducting, seals, and fan circuits. A square cartridge could not replace a cylinder in the normal holder. The popular metaphor hides the real engineering. Nobody carved the box into a cylinder. They exposed one face to cabin air, sealed the rest, and connected its outlet to a lunar module suit hose. The problem was pressure, leakage, and airflow, not geometry alone. The secondary lunar module cartridge was selected at about 85.5 hours. As the crew stretched the remaining capacity, the maximum indicated carbon dioxide partial pressure reached 14.9 millimeters of mercury. Command module cartridges sat only meters away, chemically useful and mechanically stranded. Every improvised connection carried a second risk. If air leaked around the lithium hydroxide instead of through it, the fan could run while the cabin kept accumulating carbon dioxide. If the restriction was wrong, the suit circuit compressors would operate outside the intended load. An adapter that looked convincing was worthless. The ground had to prove that a build made from flight materials would actually move enough air through the absorbent. In Houston, NASA's Crew Systems Division reproduced the problem using flight hardware. Its own report defined the constraints. The arrangement had to work. It could use only materials available to the crew, and it had to be simple enough to describe over the radio without dangerous ambiguity. The team selected an inner plastic stowage bag from a liquid cooling garment package, a stiff lunar module cue card, special gray tape carried on board, and the lunar module suit hoses. Then they assembled the proposed adapter on the ground. This was not a craft demonstration beside mission control. The prototype would be tested as part of the environmental control system it was meant to modify. Take one box-shaped command module cartridge, wrap tape belts around it with the sticky side outward without blocking the screens. Plug the central bypass opening with towel. Bend the cue card into an arch so the plastic cannot collapse against the intake. Pull the inner stowage bag over the cartridge and arch, then pleat and tape it airtight. Cut one corner, insert a separated suit hose, and seal the joint. When the fan runs, cabin air passes through the lithium hydroxide, collects inside the bag, and leaves through the hose. 2 adapters feed the suit loop. Tape partly covers the blue outlets, so the compressors see the correct load. The card gives shape. The bag defines the air path. The tape makes it airtight.
NASA placed the modified cartridges in the Crew Systems Division's 11-foot chamber, configured as a simulated lunar module cabin. Carbon dioxide was injected to imitate the crew's metabolic output. Engineers measured cabin concentration, system concentration, pressure differences, and breakthrough time. The purpose was larger than asking whether the first cartridge worked. The test had to establish when cartridges would saturate and when the crew should add replacements. That timing reduced the need for continuous telemetry, important because telemetry itself consumed power Aquarius could barely spare. The test showed the arrangement would provide more than enough carbon dioxide removal for the return. Only after the airflow and timing had been demonstrated were the construction details relayed to Apollo 13.
At about 90 hours into the mission, Capcom Joe Kerwin began reading the construction procedure to Jack Swigert. Lovell gathered materials, Haise assisted nearby, and Swigert performed most of the narrated assembly. The result looked improvised because it was improvised, but its mechanism was no longer a guess. Ground and spacecraft now held versions of the same system. The official test report records the flight vehicle's carbon dioxide concentration rising to about 15 millimeters of mercury, then falling to 0.2 after the adapters went into service. That drop is the evidence. The square cartridge never became a lunar module cartridge. The bag, arch, seal, and hose made the cabin air behave as if the incompatible hardware belonged there. The first pair of command module cartridges operated for roughly 20 hours. Then a second unit was stacked onto each original cartridge to extend removal capacity. During the period when only the supplemental command module cartridges were working, the mission report says indicated carbon dioxide remained between 0.1 and 1.8 millimeters of mercury. The adapter became routine life support, monitored, changed, and managed beside every other scarce resource. It did not repair the oxygen tank, recharge the batteries, correct the trajectory, or prepare Odyssey for re-entry. It removed one lethal constraint well enough that the teams could continue solving the others. Apollo 13 splashed down on the 17th of April. The crew survived because a chain of spacecraft, procedures, simulations, and people kept replacing failed assumptions with workable ones. The mailbox is the most tangible piece of that chain. Plastic, a procedure cover, tape, a hose, and a cartridge. But its lesson is not that anything can be fixed with duct tape. The ground team understood the interface, reproduced the environment, measured the airflow, established the replacement interval, and gave the crew a procedure they could build. Under pressure, improvisation was not the opposite of engineering. It was engineering performed before the design had time to become a product.